Hi everyone, welcome to Atmospheric Dynamics. This video will cover unbalanced flows. So we're going to look at a couple different topics in unbalanced flow. We're going to start out with the Isallobaric wind. After that, we're going to work our way through ageostrophic winds. And then finally, we're going to talk about the concept of geostrophic adjustment. So first off, Isallobaric wind, it's a big word. What does Isallobaric mean? Well, what the Isallobaric wind is, it's an unbalanced wind, since we are talking about unbalanced flows, that result from the gradient of the pressure tendency. So this is a wind that's unbalanced, and unbalanced means that there's an acceleration. Throughout our previous discussions of winds, we were looking at balanced flows where the winds were not accelerating or they were only accelerating in direction by changing direction. Now we're looking at changing wind speed. So what exactly is an isalobar? It's an isopleth. It's a line of constant something. In this case, it's a line of constant pressure changes. So by definition, it says it's an isopleth that connects places having equal changes in atmospheric pressure within a given period of time. So at a given location, pressure changes, and if we can compare all those pressure changes, the pressure changes that are all the same, we're going to draw a line, an isopleth, that connects those. So this is what the pressure changes look like. When you look at a surface chart or look at METARs, remember we talked about METARs in the remarks section. The 5 group tells you how much the pressure changed. And they also plot this on surface charts. And the changes can be positive or negative depending upon whether pressure is rising in the past 3 hours or if pressure is falling. And these values are plotted in whole units and tenths of millibars. So where you see 20 or plus 20, that means the pressure rose in the last 3 hours 2 millibars. And where you see negative values, that means the pressure fell over the past 3 hours. So if you remember from our discussion on temperature advection and also vorticity advection, we had an equation that related local changes to advection. And we're going to try that with pressure now. We're going to say that in a local area and a given location, pressure changes can be resulting from weather systems that are moving in, which is the advection of pressure systems or advection of pressure, and also as a result of the parcel changes, meaning that as you move along with a parcel of air, the pressure is either increasing or decreasing because of weather systems, because the weather system is getting stronger or getting weaker. So that's the advection or the local change as a result of these two different things. What we're going to assume in the Isallobaric wind is that we don't have any pressure advection, meaning that weather systems are not moving. That's a bad assumption. Weather systems, as you know, moves, but we've got to get a handle on this somehow. So we're going to make some very, very simple assumptions, and we're going to say that the local changes in pressure are a result of the weather system either intensifying or detensifying, either deepening or filling. So that's what the parcel change is. So no advection. Kind of strange, but we're going to go with it. So if we drew weather systems, if we looked at a surface chart, this is a pretty simplistic surface chart. We see that we have a high and low pressure system. And if we draw isolobars, once again, isolobars are lines of constant pressure change. Now these isolobars are not because the weather system is moving, it's just that in these areas the weather system is either intensifying or it's filling. So you can see to the east of this low pressure system, it's intensifying. You notice that the pressure is dropping. And to the east of the high, the weather system also is intensifying in that the high is getting stronger. So from our horizontal equation of motion, we're going to assume that the flow is frictionless. That's one assumption. And then if we do that, you can remember that we can break our components of the equation of motion into the x direction and y direction. Notice that we're keeping the acceleration term in this case. Now this is your horizontal equation of motion in Cartesian coordinates, not natural, but Cartesian coordinates, so you can see that there's x and y. And we're using height as a vertical coordinate, meaning that you're on a constant altitude chart and not a constant pressure chart. So what we're going to do is we're going to take this equation and solve it for the geostrophic wind. And remember, our assumption for the geostrophic wind was that there was no acceleration. So when we throw the acceleration terms out, we're left with 0 on one side and FV minus 1 over rho dP dx for one equation, and minus FU minus 1 over rho dP dy in the other equation. So what we're going to do is we're going to bring those terms over to the other side, the FV and the FU, and then we're going to divide both equations by F, which gives us the geostrophic wind. And we've done this before. You've seen this in our derivation for the geostrophic wind. So this is just what the geostrophic wind looks like. So now that we have the geostrophic wind, we are going to manipulate it a little bit. What we're going to do is we're going to take the geostrophic wind and take the derivative with respect to time. So in the x direction, we'll have VGO, or the derivative of the geostrophic wind, V, with time. And we'll do it with the y direction also. When we do that, we also have to take the derivative of the right-hand equation, or the right-hand parts. So you'll have a ddt on both sides. So what we're going to do now is we are going to take that equation, we just took the time derivative, and we're going to swap the time derivative. And we can do this. We're going to do that with the derivative with respect to x of the pressure. So in other words, for the first equation, we had the derivative with respect to time of dp dx. Well, we're going to swap that derivative and pull the x out and put the t inside of that parentheses. So now we have, for both equations, the x direction and the y direction, something that looks like dp dt. And that dp dt, what that means is the change of pressure with time. And that's what we measure in our METARs with at stations that measure, that have ASOS or AWOS machines. They can measure the change in pressure with time. Now on the outside we have dp dx, or actually we have ddx and ddy, which means it's the change in the x direction and the change in y direction of dp dt. dp dt, the change of pressure, and ddx, ddy is how the pressure changes are occurring in the x direction and in the y direction. I know that sounds kind of confusing. So we measure pressure changes, dp dt, and what the derivative with respect to x and the derivative with respect to y represent are the gradients in the change of pressure, and in each direction, in the x direction and the y direction. So in other words, if we can draw isolobars, if we can draw changes in pressure with time, connect all those lines, and see what the gradient looks like, in other words, the gradient in the isolobars, that'll give us an accelerating wind. So on a weather chart, a simplified weather chart, this is what it looks like. We drew our isolobars. These are measurements of the change in pressure with time. And if we can see how it changes in the x direction and y direction, we'll be able to figure out the acceleration of the wind. So what we have now is an accelerating wind, which we're going to call the Isallobaric wind. And we have two components of that wind, the U and V components. Now remember, U is actually du dt, and V is actually dv dt, accelerating. I just put in U or V to make it simple. And you can see that it's a result of the gradient of the pressure change. dp dt is the change in pressure at a given location, and ddx and of course ddy are the gradients, how the pressure changes in the x direction and the y direction. That's the Isallobaric gradient. So this wind, of course, is not geostrophic because it's an accelerating wind. And it depends upon the Isallobaric gradient. And in other words, the wind blows in towards dropping pressure and out from rising pressure. So these are winds that will accelerate, and typically you'll see these with an intense weather system, a weather system that's intensifying. So here's an example. This is a day back in 2010 when we had probably the lowest pressure in North America at this time. Very low, very strong low pressure system that was intensifying across the upper Midwest, across North Dakota, Minnesota, and Ontario. And here are the pressure changes. You can see that there are isolobars, lower pressure falls or low pressure falls. Pressures are falling in Ontario and rising across Iowa and Wisconsin. So there's a very strong gradient. And with that strong gradient, we had very strong winds, winds that were sustained at about 30 to 35 knots across the region. And we can see that there were very strong gusts associated with that. And those gusts typically are associated with accelerating winds. So the point I'm trying to make is that typically when you have these very strong pressure changes, these Isallobaric gradients, it results in accelerating winds and you'll have very gusty conditions. So in summary, we've just added another wind. We went through all these other winds before. They were balanced. The Isallobaric wind is an unbalanced wind. It's an accelerating one where there is no friction and no advection of pressure. Pressure systems don't move. And the balance, of course, there's no balance. This wind accelerates. And then finally, it approximates weather systems that are developing. So that is the Isallobaric wind.